Okay, this is example number 8 from section 13.5. We have a boy that is swinging and has a weight of 60 pounds. So we have a weight of 60 pounds. And at the instant shown, the center of mass of the boy, right there, has a speed of 15 feet over second. So we know that the velocity is always tangent to the trajectory. So, and the trajectory is, this is the trajectory of the boy. So we have a velocity right here, velocity equals to 15 feet per second. And we are asked to find the tension of the two chords. So we have to imagine that the kid is singing, is sliding in a swing, and that has two chords, one in each side, and the rate of increase of his speed at that instant. So we are given the velocity, and we are asked to find the acceleration and the tension of the chords. So first of the things we have to do is decide which system of reference we will use, the system of coordinates we will use. And since we have a circular path and we are given the velocity, the proper coordinate system to use is the tangent normal system. So I'm going to draw here my system. This is the tangent direction, and this is the normal direction. You know that the normal direction always points towards the center of the radius of curvature of my trajectory. So here is also given that the radius of the trajectory is 10 feet. So I know the radius of curvature for that instant. And well, this is a circular path, so that radius is constant. You can have problems where that radius is not constant. So the curve can be in any shape, and we can have a variable radius of curvature, right? But in this case, we have a constant radius of curvature. So what is the solution? First of all, we have to draw our free body diagram of our boy. I'm going to, instead of drawing the whole boy, I'm going to draw a particle only for the center of gravity. This is my weight of the boy, which is 60 pounds. And then I have the tension of the chord. And actually, instead of driving only one chord, I'm going to write two tensions, because we are asked to find the tension of the two chords to find. So this is the free body diagram, and we have to draw my kinetic diagrams as well. Since we have a curve trajectory, we have a tangent acceleration and we have a normal acceleration. So my tangent acceleration and my normal acceleration. And we know that the normal acceleration is the velocity squared over radius of curvature, and our tangent acceleration is just actually is the rate of increase of speed. So here is what we have to find, that's how that speed that we are given change over time, or is changing actually instantaneously in this picture of the boy when the angle is 60. So we are given this angle 60 degrees. So now that we have the free body diagram and the kinetic diagram, we apply our equations of motion. And we know that forces in the normal direction are equals to the accelerations in the normal direction. So if we draw our coordinate system right here, this is the normal and this is the tangential, right? So we need to have that angle here. We know this angle right here is 60. So this angle right here is also 60. So we have here in the normal component, we have 2t minus the weight times sine of 60 degrees is equals to the mass. The mass, we have to derive the mass from the weight remember, for the American units, the weight is a primary unit and the mass is a derived unit. So we have to divide the weight times the gravity to find that mass. And we know that the normal acceleration, we already wrote it right here, is the mass times the velocity, which is given, square, over the radius of curvature, which is 10. So that's my first equation, and here, as you see, we have only one unknown, and we can find the two chords. So the two chords will be all that expression. So here we find that the tension is equals to 46.9 pounds. In the case of the rate of change of velocity, now we add forces in the tangential direction, and that will be mass times tangential. What do we have in the tangential direction? So the two chords are perpendicular to the tangential direction, so they don't act, they don't contribute. So we actually only have 60 cosine of 60 degrees, and that's equals to the mass, which we already know is 60 divided by 32.2 times the rate of change of the velocity. So from here, the change of velocity is equals to 6.1 feet over second